Okay, so what we're going to do is to show that the determinant of the product is the product of determinants. So we've kind of already talked about this when thinking about elementary matrices. We saw that doing a type 1 matrix swaps the negates the determinant. So to see how kind of this plays a role in this factor, let's think about what the determinant of a type 1 matrix is, type 1 elementary matrix. So let's do kind of like do an example. Let's do like let's do a 3x3. Let's say E is the 3x3, and can someone give me a row swap, a random row swap? Oh, that's the actual matrix. Cool. 1, 0, 0, 0, 0, 1, and 0, 1, 0. Okay, what is that row swap? Row 2 to row 3. All right, can you guess, can you look at the determinant? What is the determinant, just clearly? Do this like by inspection. -1, yeah. All right, determinant, and the determinant of this 2x2 is -1. So determinant of this is -1. Right, 1 times 0 minus 1. Yeah. So if you think about it, like the determinants of all of these type 1s will be negative, right? When you do the so if you row swap any other two, there will always be a 1, and then always times a 0, 1, 1, 0, right? And if it's not like that, so yeah, what would an example be where it's not like that, where you have where you're the term the what is this? This is M11, right? Can you give an example where M11 is not 0, 1, 1, 0? Let's just go through the row swaps. Let's do row 1 swap row 2. What does that matrix look like? Yeah, 0, 1, 0, 1, 0, 0, and 0, 0, 1. Yeah, so actually I meant to say that it's always going to be a 1 times right? It's always going to be this, and then times your M is always going to be 0, 1, 1, 0, right? This is what M is this? Three, yeah. And so question, why is it, so remember in our cofactor, remember it's -1 to the I plus j, a I j, oops, a I j, and then determinant of m I j, right? So why is it always a positive 1 times a 0, 1, 1, 0? Right, sometimes we have this -1 to the I plus j thing over here, right? Someone say why it's always going to be a positive one. So when you do the determinant, when you calculate the determinant, for an arbitrarily sized matrix, right? Why is that -1 to the I plus j always positive? Yeah. So odd plus odd, it's either odd plus odd or even plus even, right? Because I plus j is always even. In fact, so you can make it. You can make I plus j always even. In fact, I is equal to j, right? I equals j. You can always pick one on the diagonal, right? When you do a row swap, there's always going to be one term when it's 3 or higher that's on the diagonal, and then you're looking at the dimension small. So if you kind of expand that to 4x4s and higher, it's kind of like an induction from there that it's always going to be like this. When you do your cofactor expansion, you'll always pick one on the diagonal, and then the m for that term will look like a row swap matrix in one smaller dimension. So let's do an example. Like, let's say we have 4x4, and let's say we do row 2 to swap row 4. Just for example, that's not a midterm problem, is it? Just make sure. No, that is not a midterm problem. Okay, can someone tell me this matrix? Yep, 1 0 0 0 0 0 0 1 0 0 1 0, and then 0 1 0 0. So why don't we, because it's kind of easier when we do it here, it's easier to see. For the sake of practice, let's do a cofactor expansion on this element. So what is the cofactor? So the determinant is equal to, since the only term, everything else is 0, it's going to be -1 to the 3 plus 3, A33, determinant of M33. So this is 3 plus 3 is even, 1. And then can someone read out for me M33? Got a lot of 1s and 0s there. 1 0 0 0 0 1 0 1 0. Now we know this determinant is -1 because this is a row swap matrix. This is a type 1 in 3x3, which we already proved. Right? So when you go in higher and higher dimensions, determining if the calculating the determinant will always affect the determinant in will be dependent on determinant in a smaller dimension. So if you can do this for 3x3s, that means you can do it for 4x4s and forever. So if E is type 1, then the determinant of E is equal to -1. So what does that mean? So we saw that the determinant of EA when E is type 1 is equal to determinant of E, well, I should say it's equal to negative determinant of A, right? That's what we said this last time, right? But we just showed that determinant of E is equal to -1. So this is really determinant of E times determinant of A, right? Just substituting -1 into determinant of E. Does that make sense? All right, cool. So let's do for type 2s. So what is a type 2? Let's do rho I to rho alpha rho I. And let's take the determinant. So first of all, let's look at the determinant of A is equal to, so our determinant formula is K equals 1 to N. And why don't we do our expansion on rho I? So it would be -1. You tell me, if you expand on rho I, what are our indices? So we're expanding cofactor expand on rho I. So what's the first term in the sum? I'm doing cofactor expansion on rho I. Okay, we can also express this as the cofactor, right? And if you're expanding on rho I, you're fixing I and you're going along K, different columns. All right, so what are the indices? What are the what coordinates go here? What coordinates? Did we forget? Right, silence. Right, it's I plus K, I K, I K, right? Midterm on this stuff. All right, so let's compare that with the determinant of EA, where E is this type 2 that does, where E is rho I to alpha rho I. So we'll have the same thing, -1 to the I plus K. Now, what is going to be, so in the AIK component, we're multiplying by alpha, right? And we're multiplying on rho I. So every term in rho I, it's multiplied by alpha. Now, can someone tell me why I didn't bother looking at, why doesn't this change? So I have this big matrix And I have this row. Here's alpha A1, alpha A2, alpha AN. Why are these terms the same? Someone remind me what the big M means? It's deleted, right? Row I is always deleted. And row I is precisely the elements that are changed, right? So of course those would be the same. So now, only thing that's different is this alpha. So let's bring it outside. It's all a product inside the sum. So that's it. And this was determinant of A. Okay, so, and we saw from last time that the determinant of E, the thing that does multiplies a row by alpha is alpha. So the determinant of E alpha is equal to determinant of E times determinant of alpha of A. We're substituting now alpha in for E. Okay, questions about that one? All right. So we had that, we also had the type 3s that do not change the determinant, right? And we saw that the determinant of type 3 was equal to 1. So if you do determinant of EA, it's determinant of A, but determinant of E is just 1, so we can just tap that in there. So nothing much to say about that one. Okay, so why is this so important? Can someone kind of guess why? If we can say that this is true for elementary matrices, why can we do it for all matrices? What is nice about elementary matrices? What are elementary matrices? What do we know about elementary matrices? Tell me some things you know about elementary matrices with respect to inverses. How do elementary matrices play a role in the inverse of a matrix? We use them to find inverses. What else? If A is non-singular, then what do you know about A? As an inverse, yeah. What's another, yeah, if we convert to elementary matrices, A can be factored. Right, why is that true? Is because it's row equivalent to I. So let's think about that. So if we have determinant of AB, and let's say A and B are non-singular, Then this is just determinant of some e's that make up A. And some e's, we'll say, let's say maybe F, elementary matrices that make up B. Does that make sense? See why I can do that? Yeah, so now we've just expressed this whole thing as a bunch of elementary matrices, but we just showed that if we have an elementary matrix times something, then we can split up the determinant. So this is en minus 1, so calculating the determinant is just calculating the determinant of all these little things. And now, if you think about it, we can go backwards. If we have the determinant product of determinants, we can go backward and say this as the determinant of a product. So now we can go back to determinant of this en to e1 and determinant of fm to f1. So this makes determinant of A and determinant of B. So that's just if they're non-singular, right? Okay, does that make sense? Like if we know it's true for elementary matrices, then, well, because all matrices, have some decomposition, then it's true. Okay, let's think about, well, what if A is singular? Let's say B is non-singular. Let's think about the determinant of AB. So now I can't express A as a product of elementary matrices, right? However, what can I say about elementary matrices with respect to A? So A is not row equivalent to I. What is it row equivalent to? Not to B. B is non-singular. So what is the reduced row echelon form of A? So remember, saying row equivalent, good, yeah. So it's reduced row echelon form has a row of zeros. Okay, so let's think about that. Let's say A is equal to a bunch of E's, but instead of times the identity, it's multiplied by some, let's call it R, where this has a row of zeros. Okay, so let me ask you this. I have En to E1 times R times B. What do you know about the product RB? If R has a row full of 0, what do you know about the product RB? Also has a row full of zeros. Has a row full of zeros. Why is that? Just matrix multiplication, right? All right, cool. All right, now let's say, so let's keep that in mind. Let's assume AB. So you tell. So if I'm almost out of time. If determinant of AB is not equal to determinant of A, determinant of B, what does that mean by the determinant of the product? So first of all, what's the determinant of A? Zero. So if we're saying that the determinant of the product is not the product of determinants, that would imply that determinant of AB is not equal to zero, right? So if it's not equal to zero, it's non-singular, right? So if we're doing like a contradiction, so suppose AB is non-singular. That means that we can do we can find some product that we can find some matrix F such that the inverse is equal to identity. So now, if we multiply through, we have RB is equal to, let's see, E1 inverse, E2 inverse, En inverse, and then F inverse. And how do you solve for R? Well, actually, it's fine. RB is fine. RB has a row full of zeros. Why is that impossible? This can't have a row of zeros, right? Why not? This is non-singular. The whole thing is non-singular, so it can't have a row of zeros. So that's a contradiction. That means that determinant of AB must equal zero. So determinant of AB is equal to determinant of A, which is zero, times determinant of B. So yeah, that's it. You can do the same thing if they're both singular. You have a similar kind of deal in terms of rows of zeros, which causes the contradiction. But yeah, that's all that was left over. We did a lot of 2.2 actually when talking about elementary matrices. The only thing we hadn't really said was that talking about the determinant of a product. So that's it. This is true for all matrices. So for all n by n matrices, the determinant of a product is just the product of the determinants. That's the main takeaway from that. Okay, so that's all I want to talk about for today. We're over now. So I guess I'll stop recording.